Welcome to AudioCert, where the official study guides are brought to life. Today we're taking a necessary, really rigorous deep dive. We're looking into the foundation of cloud governance and risk management within the Certified Cloud Security Professional, or CCSP, curriculum. The topic, data classification. And this isn't just, ticking a box for compliance. It's really the absolute operational bedrock. Every successful cloud security strategy, it's built on this. So our mission today is to really unpack this truth. Data is your most critical asset, period. And effective security, well, it relies entirely on knowing exactly what data you have, where it lives logically and physically, and understanding its precise value and, crucially, the legal obligations tied to it. We're going to map out the essential processes, the defining policies, those critical roles, and the complex legal and technical challenges you face managing that data asset securely, especially in the cloud, right? That multi-tenant, borderless environment.
Absolutely. And that mission statement is spot on because classification really is the keystone. If you grasp this chapter, you immediately start seeing connections across the entire certification body. It's fundamental. We kick off with the secure data lifecycle from Domain 1, then we link straight into the core security controls of Domain 2, and from there, it feeds directly into the audit mechanisms in Domain 3 and also the necessary security operations we talk about in Domain 5. But honestly, the real weight of classification, it falls squarely on Domain 6, legal, risk, and compliance. Big time. Think about it, how long you keep data, how you encrypt it, which regulations apply. It all flows from that initial classification decision. So yeah, we're covering the whole spectrum today, everything from who legally owns the data right down to the highly technical, often misunderstood ways you actually destroy it securely.
And for you, the listener, this deep dive gives you that strategic insight you absolutely need. You just can't afford financially or operationally to slap the highest level of security on every single bit of data, maximum encryption, constant auditing, endless storage.
Right, that's just resource exhaustion waiting to happen. It's unsustainable.
Exactly. Mastering data classification is really the only way to properly apportion those security resources.
Yeah.
It's how you achieve demonstrable compliance in today's, let's face it, incredibly complex multi-jurisdictional cloud landscape. So let's unpack this.
Okay. We should start where all successful security programs have to start, with data inventory. It sounds basic, but it's foundational. You simply cannot classify, control, or protect what you don't know you possess. It's step one. And as soon as you inventory an asset, you have to assign immediate legal and administrative responsibilities to it. No delay. Because we're talking about the cloud here, right? Custody shifts around constantly. Defining these roles clearly is absolutely critical.
Right. And we have this kind of essential trio of roles. They define who gets the budget, who sets the policy, and maybe most importantly, who ends up shouldering the legal risk if things go wrong. The first one, the one with the most responsibility, is the data owner. This is usually the organization, the company, the university, the government agency that collected, created, or maybe commissioned the data in the first place. In the cloud world, the cloud customer is almost always the data owner.
Overwhelmingly, yes.
And within that organization, the owner might be an individual, like a department head, or maybe a specific business unit manager. They're the ones making the executive calls about the data's value and the ultimate protection strategy. And internationally, especially under rules like the EU's GDPR, that's the General Data Protection Regulation, they often call this role the data controller. They control the purpose and the means of the processing.
Exactly. Then next up, you've got the data custodian. This is the person, or maybe the team, tasked with the day-to-day hands-on stuff, the maintenance, the administration, applying the security controls. But always, as mandated by the data owner or controller, they are the implementers, the doers. Think of your database administrator, maybe a cloud security engineer, or the team making sure encryption gets applied correctly and backups actually run. They handle the mechanics.
Okay, owner custodian. And then the third is the data processor. This is the organization, or maybe a person, who actually performs the actions on the data. Things like copying, storing, destroying, manipulating, moving it around.
Yeah.
But always on behalf of the data owner. And the classic example here is the cloud provider itself.
Yeah.
Whether it's infrastructure as a service, platform as a service, PaaS, or software as a service, SecOps, they are pretty much the quintessential data processor. What I always find kind of staggering is that legal reality you touched on earlier. So let me get this straight. If my company, the data owner, uses cloud provider A, who's our processor, and they then subcontract storage out to, say, a managed service provider, processor B, maybe in a totally different country.
Yep, happens all the time.
And that third party gets breached.
Right.
The legal responsibility, the liability still falls entirely on me, the original data owner.
Yeah.
Seriously. How do we even begin to manage that kind of risk down the chain?
That really is the crux of the data controller's liability, and it perfectly highlights why classification is so incredibly important. Data owners remain legally responsible for all the data they own, full stop. The legal obligation to protect it doesn't just vanish because it left your physical data center. This is why you need really stringent contractual requirements. These are usually detailed in something called a data processing agreement, or DPA. That DPA has to mandate specific security duties, and crucially, it needs to grant the data owner explicit audit rights over the entire supply chain. That includes any subcontractors. If you classify data as, say, highly regulated, maybe it's financial data or health data, you absolutely must ensure your contracts allow you to verify the security posture of any subsequent subprocessors down the line. If you can't, well, you're carrying enormous, potentially business-ending risk.
Wow. Okay. And just to make things a bit more complicated, these rules aren't always fixed, right? They're relative to the specific data set.
Exactly right. It's contextual.
So the cloud provider is the processor for our customer data, the data we put in their cloud. But the moment that same provider collects its own data, maybe it's employee HR records or its own customer billing information or its own proprietary software code, for that specific data, the provider suddenly flips roles. They become the data owner for their own stuff.
Precisely. The roles are defined by the relationship to a particular data set.
Okay, so now we know who owns it, who controls it, who processes it. Let's track its journey. The data lifecycle is another really crucial concept here. It maps out the sequential phases data moves through, basically from birth to death. It's often shown as a cycle, maybe 6 phases. The journey starts, naturally, with create. This is the instant the data comes into existence. And you could argue this is the most important phase because this is where the data owner must be identified and, crucially, where that initial classification and labeling has to happen.
Absolutely critical point. If you miss it here, if you don't classify and label at creation, you spend the rest of the data's life cycle just playing catch-up. It's much harder, much more expensive later on. So after create comes store. Seems simple, right? But in the cloud, store brings immediate challenges. You need to address encryption, not just at rest, but often in use as well. And think about the cloud risks here. Your data is often replicated across multiple geographic regions for resilience, which is good for availability, but you, the customer, might not even know the physical location of all those copies. That immediately impacts jurisdictional compliance. Plus, there's multi-tenancy. Your data is sharing physical hardware, storage, network components with other customers. That requires strong logical separation controls from the provider.
Okay, so after storing it, we hit the use phase. This is where the data is actively being accessed, maybe modified, processed in some way.
Yeah.
The security challenges here involve applying policies like separation of duties, least privilege access, making sure people only see and do what they absolutely need to.
And don't forget data remnants. If data is actively being used in memory, say in RAM, or maybe written to temporary files during processing, you have to consider the remnants left behind after the process finishes. That can be a subtle but serious vulnerability many organizations overlook. Then comes share. And wow, in the cloud, this phase has just exploded in complexity. We're often talking about system-to-system sharing across completely different platforms, maybe a multi-cloud setup or a hybrid environment connecting on-prem to cloud. Sharing demands that you clearly define trust boundaries and security zones. If you're sharing classified data with a business partner, how do you know? How do you ensure their security controls are equivalent to yours?
Right. That's a huge challenge.
It is. And this is where proper data mapping becomes absolutely essential. We'll dig into that a bit more soon.
Okay, phase 5 is archive. So the data isn't needed for immediate production or daily use anymore, but maybe legal requirements or regulatory rules or just historical value means it still has to be kept. It usually moves to a lower cost storage tier, maybe something with slower access times.
Exactly. And archiving requires clearly defined retention periods. How long must it be kept? And just as important, verification that the long-term encryption keys used for the archive remain protected and, crucially, accessible. You don't want to find out years later you can't decrypt your own archive. And finally, all data must eventually reach the destroy phase. This is where it's permanently and securely disposed of, rendered ideally mathematically unrecoverable. And as we'll discuss in depth later in the cloud, this phase is exceptionally technical. It requires methods far beyond just hitting delete or traditional disk wiping.
So to manage this whole flow, especially when data is moving between maybe different cloud environments or partners, you really need a visual map, right?
Yeah.
That's where data flow diagrams or DFDs come into play. It's a classic systems engineering tool, but incredibly useful here. It visually shows the process steps data takes as it moves through a system or between systems.
Their value is really twofold, especially in the cloud context. First, DFDs help you establish functional requirements before you even think about selecting specific technologies. For instance, if your DFD clearly shows that customer payment data must pass through an external third-party payment processor, well, you know immediately that one of your core functional requirements is PCI Data Security Standard compliance. You then build or select your environment and controls around that requirement, not the other way around. You don't pick a tool and then try to make it compliant.
That makes sense. Requirements first.
Exactly. And second, particularly in a multi-cloud or hybrid scenario, DFDs are indispensable for figuring out where to place your controls. Imagine a DFD showing data moving from a secure, private database running in cloud provider A over to a public-facing analytics engine hosted by cloud provider B. The DFD instantly highlights that transition point. Maybe it's an API call or data moving through a storage gateway. That's the point where the data leaves your more trusted, protected zone. That exact point on the diagram dictates your mandatory control requirement. Maybe it's mandatory data masking or tokenization or specific encryption before the data even begins transit. Without that DFD, you'd largely be guessing where you, the customer, need to augment the provider's built-in controls.
Okay, that visualization piece seems really key for complex environments. Now let's tackle some terminology that often causes confusion. Categorization, classification, and labeling. People tend to use these interchangeably out in the wild, but for the CCSP exam, and more importantly, for building a robust, enforceable policy, we need to draw some clear lines, right?
Correct. It's important to be precise here, even if the industry isn't always. Following the book's convention, we use categorization based on the data's use. It answers the question, how is this data going to be utilized, or what external rules govern it? So, this is where we might categorize data by regulatory compliance. Is it governed by HIPAA for health data? GLBA for financial stuff, PCI DSS for credit card numbers, or maybe the big one, GDPR for personal data of EU residents. Or we could categorize it differently, maybe by business function, like marketing data, HR data, research data, or even by project. Categorization helps define the overall scope of your data management policy, which rules apply to which broad sets of data.
Okay, so categorization is about use and external rules. Then, in sharp contrast, classification is defined by a specific trait or characteristic that's inherent to the data itself.
That's the distinction.
And these traits are generally things like sensitivity, jurisdiction, or criticality. The result of the classification, the level assigned, dictates the level of security control required. High sensitivity means high security controls.
Exactly. Classification drives the protection level.
And the really crucial takeaway here, and this applies to both categorization and classification, is the absolute need for uniformity. Whatever system you choose, maybe it's a simple 2-tier model, maybe a more granular 5-tier model, it must be adopted and enforced uniformly across the entire organization. No exceptions.
You nailed it. If one department classifies customer emails as, say, internal use only, while another department labels the exact same kind of emails as confidential, you've got inconsistent enforcement. That's a massive security hole and an auditor's nightmare. Uniformity is paramount. So, let's dig into those 3 main classification types a bit deeper. We'll start with sensitivity. This is probably the most common model people encounter. It's often analogized to the U.S. military system, top secret, secret, confidential, unclassified. Data gets classified based on the potential negative impact of damage that unauthorized disclosure would cause to the organization, or perhaps to the data subjects themselves. And importantly, under this model, you're generally required to classify and label all data. Everything gets a label.
Even if it's basically public information.
Yes, even then, you have to assign a label, even if it's in the negative. If disclosure poses no harm, it still receives the unclassified or maybe public designation. Why? It prevents auditors or assessors from finding chunks of unlabeled data and just assuming it was forgotten or overlooked. It shows intent. Everything has been assessed.
Okay, that makes sense. No ambiguity. Next up is jurisdiction. And this is where the cloud complexity really kicks into high gear, isn't it?
Oh, absolutely. The physical location where the data is stored, or perhaps more accurately, the location of the data subject, the person the data is about, dictates its legal treatment. And the differences globally can be huge. The contrast between, say, the EU approach and the US approach is particularly stark.
Right. The EU, primarily through GDPR, takes this really sweeping, comprehensive approach. It's focused on fundamental rights protection for the individual, the data subject. And importantly, those rights follow the data, regardless of where the company processing it is located.
Whereas the US, well, it tends to rely more on industry-specific laws at the federal level. You've got HIPAA for health information, GLBA for financial data. but there are significant gaps when it comes to general personal data protection federally.
Yeah.
State laws, like in California, are starting to fill that, but it's patchwork.
And this really brings personally identifiable information, or PII, into sharp focus. Protecting PII is often the core issue in these international data transfer disputes.
Definitely. And just defining what constitutes PII consistently across borders is a massive challenge in itself. What's considered PII in one country might not be in another. This often forces multinational organizations to adopt the highest common denominator standard for protection just to be safe everywhere. Okay, the third main classification type is criticality. This classification isn't driven by regulation or sensitivity to disclosure, but rather by the organization's own business impact analysis, the BIA. Critical data is the data that is absolutely essential for the organization's survival. If this data is lost or unavailable, the business might cease to function.
So for a bank, maybe that's the live transaction data?
Could be. Or for a pharmaceutical company, it might be their proprietary chemical formulas. For an e-commerce site, maybe the current inventory database?
Right. It's the must-have data.
Exactly. This classification directly drives decisions about things like backup frequency, recovery time objectives, RTOs, and failover requirements. It gets the highest level of availability protection.
Okay, so we've categorized and classified our data, but we live in a world where data gets shared, right? Mergers happen, acquisitions, partnerships, or just moving data between different internal systems. This means we need data mapping. Talk about that.
Data mapping becomes necessary when you need to ensure that classification levels are understood and respected across different systems or organizations that might use different schemes. Let's say your system uses a 5-tier classification model, Tier 1 being the highest sensitivity, and you need to share data with a partner whose system uses a simpler 3-tier model, high, medium, low.
How do you make sure your Tier 1 data is treated as high in their system?
That's exactly what data mapping does. It's the process of formally translating and normalizing those classification levels so they remain meaningful and enforceable when data moves. You need to ensure that data recognized as, say, highly restricted in System A is automatically recognized and, more importantly, protected as such by the receiving System B. This often involves creating documented translation tables and ensuring you have consistent metadata tagging that travels with the data to prevent any security degradation during transit or once it lands in the destination system.
Gotcha. So it prevents things falling through the cracks during transfers.
Precisely. And all this rigorous work, inventory, categorization, classification, mapping, culminates in labeling. Labeling should happen immediately, right back in the create phase of the life cycle. And the label itself needs to have certain qualities. It must be enduring, it sticks with the data, easily understandable by both humans and machines, and, as we said, consistent across the organization.
For physical documents, that's pretty straightforward, right? A header, a footer, or maybe a watermark. But in the cloud, it's all digital. How does that work?
Yeah, for electronic files, labeling usually means embedding information as metadata within the file itself, or sometimes using a very specific and consistent file name nomenclature that indicates the classification. In cloud object storage, for example, these labels are often implemented as tags or indices. This is great because it makes the data immediately searchable and allows you to enforce security policies automatically based on those tags. A good, robust label can actually contain quite a bit of detail. Things like...
Like what?
Well, the date of creation, maybe the scheduled date of destruction, definitely the confidentiality level, like secret or PII, specific handling directions, encrypt before emailing, access limitations, HR managers only, the source system it came from, the governing jurisdiction, and maybe even the specific applicable regulation, like ITAR restricted or subject to GDPR.
Wow, that's a lot of info packed into a label.
It can be. The goal is for the label to communicate all the necessary security context and handling requirements without actually disclosing the sensitive content itself.
The military cover sheet analogy used in the guide is pretty effective here. You know, the bright blue sheets for confidential, the red sheets for secret.
Exactly. That label provides immediate, instant visual communication to anyone who handles that data. It tells them exactly the security procedures required just by looking at the cover sheet, or, in our case, the digital label or tag.
But as the book points out, this is kind of a double-edged sword, isn't it?
It absolutely is. On the one hand, clear, standardized labels are essential for proper handling and security enforcement. On the other hand, if a malicious actor successfully breaches your environment, those same clear, standardized labels instantly tell them which files are the high-value targets. You've essentially put a spotlight on your crown jewels for them. It's a trade-off you manage with other controls.
Right. Makes sense. Okay, so we've classified and labeled, but all that work is kind of useless if you can't actually find the data you've so meticulously categorized later on. That brings us to data discovery. And this term actually has, what, 3 distinct meanings in the security and legal world?
That's right. It's used in a few different contexts, and it's important to know which one we're talking about. First, there's the straightforward meaning, the initial inventory process itself, discovering what data you have in the first place.
Okay.
Second, there's e-discovery. This is a specific legal term. It refers to the process of identifying, collecting, preserving, and producing electronically stored information, ESI, in response to a legal request, like during litigation or a government investigation. It's often court-ordered and has very strict rules.
And the third meaning?
The third is the more modern technical application. It's using technology, often data mining techniques and automation, to proactively find specific types of data, like classified data or sensitive PII that's already stored somewhere within your environment, maybe data that was missed during initial classification or labeling.
So when an organization needs to perform discovery, maybe for an internal audit, or maybe because they just got served with an e-discovery order, they rely on different methods. And the best method depends on how mature their classification program is, right?
Exactly. The ideal scenario, the most efficient method, is label-based discovery. If the data owners actually followed the policy, if they accurately applied those labels back in the create phase, then the organization can usually quickly and efficiently run searches based on those labels or tags. They can determine what relevant data they control, where it resides, and respond rapidly to legal requirements or security incidents. It's clean, fast, and relatively low cost.
Okay, but what if labeling wasn't perfect or wasn't done at all for some data?
Then you move to the next best option, which is often metadata-based discovery. This relies on finding data about data information that's usually created automatically by systems. Forget the simple digital camera example for a moment. Think about cloud relevance. We're talking about object storage tags, file system timestamps, maybe database schema information describing column types, or user access logs showing who touched what file when.
Ah, so you search the context around the data, not the data itself.
Precisely. You can query these metadata fields. For instance, you could search for all objects tagged as PHI that were created by someone in the marketing department within the last 90 days. It allows for highly specific searching based on attributes without having to read the actual content of every file.
Okay, label-based is best, metadata is next. What's the last resort?
The last resort, which is often highly technical and very resource-intensive, is content-based discovery. Now you are actually delving into the content of the files or data streams themselves. And this usually goes way beyond just searching for a simple keyword. It typically utilizes highly sophisticated pattern matching technologies. Think machine learning, ML models, or complex regular expressions, regex, often deployed as part of a data loss prevention DLP system.
So these tools are looking for things like credit card number formats.
Exactly. They're designed to identify known patterns, the 16-digit structure of a valid credit card number, the specific format of a social security number, maybe even specific confidential project code names, even if that data completely lacks an accompanying label or any useful metadata tag. It's powerful, but can be slow and generate false positives.
And the efficiency of any of these discovery methods seems like it would depend heavily on whether the data is structured or unstructured. That distinction comes up a lot.
It's hugely important for discovery, yes. Let's define this quickly. Structured data is data that's nicely sorted according to predefined types and attributes. The classic example is data organized neatly in rows and columns within a relational database. Every field has a defined purpose, a data type.
Like a spreadsheet, basically.
Pretty much. This kind of data is significantly easier to discover, classify, and protect because its location, format, and meaning are consistent and predictable.
Okay, so what's unstructured?
Unstructured data is, well, everything else. It's the vast ocean of unsorted data that lacks a predefined arrangement or schema. Think about the contents of a user's sent email folder, or audio files from customer service calls, video streams, a massive shared drive full of internal memos, presentations, draft documents.
Messy stuff.
Exactly. The messy stuff. And this data is far more difficult to perform discovery on because you have to rely on that deep content inspection using those sophisticated regex and ML tools we just talked about. That substantially increases the processing time, the cost, and the complexity.
And most organizations have way more unstructured data than structured, right?
Estimates vary, but yeah, it's often cited that 80% or even more of an organization's data falls into the unstructured category. That's where a lot of the risk and the discovery challenge lies.
Okay, so once we've discovered the data, the cloud gives us this incredible computing power, right? Which lets us perform really sophisticated data analytics. We can leverage the possibilities inherent in big data.
So beyond just finding the data, we want to understand it. Exactly. The overarching category here is data mining. This involves running complex queries, often using statistical models or machine learning, across various, often massive data streams, structured and unstructured combined. The goal is to detect previously unknown trends, patterns, or correlations that just wouldn't be visible if you only looked at smaller, isolated data sets.
And in security, how might that be used?
Well, data mining can be incredibly powerful for things like insider threat detection. By analyzing access patterns, data movement, maybe even communication logs over a long period, you might spot anomalous behavior that indicates a potential threat, something a simple alert wouldn't catch.
Okay. Then you also have real-time analytics. How's that different?
Real-time analytics takes those data mining concepts, but applies them concurrently, as the data is being created or used. It's about making sense of data now. This is absolutely essential for things like monitoring cloud security logs and event streams. You need to make decisions instantly, like automatically blocking an IP address that's suddenly exhibiting behavior consistent with a brute force attack. These tools rely almost entirely on automation and incredibly efficient processing.
And then the book mentions something called agile business intelligence. That sounds fancy.
It's sort of the cutting edge in analytics. These are highly recursive and iterative tools. They don't just find a trend you asked for, they're designed to find trends in trends, if that makes sense.
Kind of like meta trends.
Sort of, yeah.
Yeah.
They help identify oblique, complex patterns that maybe weren't even part of the initial query. They allow an organization to adapt its strategy much more quickly based on new, sometimes unexpected insights derived from analyzing massive amounts of both historical and very recent data together. It's about faster learning and adaptation.
Interesting. Okay, shifting gears slightly. We've classified the data, we know its value, maybe we've analyzed it. Now we need to protect its use, especially when it comes to intellectual property. That brings us to Information Rights Management, or IRM.
Right. IRM. You might hear other acronyms thrown around like DRM for digital or data rights management, or sometimes ERM for enterprise rights management. But the ISC curriculum, and generally the security field, tends to prefer IRM. Why? Because it emphasizes protecting the information itself, regardless of the file format or the device it's on. The core concept behind IRM is applying specific, granular access controls directly at the file level. These controls act in addition to whatever basic system login or network access controls you have.
So there's another layer of control on the file itself.
Exactly, and it protects specific user actions. For example, a user might be successfully authenticated into the HR system. They might have permission to open a specific salary spreadsheet. But an IRM policy applied directly to that file could prevent them from copying text out of it or printing it or maybe forwarding it in an email, even though they are allowed to view it on screen. It's very granular control over usage.
And this ties directly into protecting intellectual property, or IP. These are the valuable, intangible assets that come from creativity or invention. Security pros really need to understand the main types of legal protection for IP.
Absolutely. There are 4 key types to know.
First up, probably the most well-known, is copyright. This gives legal protection for the expression of an idea. Think literary works, music, films, photographs, software, code.
And the key word there is expression. Copyright protects the specific way an idea is expressed, the words written down, the music composed, the code typed out, not the underlying idea or concept itself. Anyone else can write a different book about the same idea.
Right. And how long does copyright last?
Typically, it lasts for the author's life plus 70 years. If it's a work for hire, something created by an employee as part of their job, for instance, then it's usually 95 years from publication or 120 years from creation, whichever is shorter.
And it grants the creator a bundle of exclusive rights, right? Like the right to perform the work, profit from it, make copies, create derivative works.
Correct. It's a significant bundle of rights. However, those rights weren't absolute. There's an important principle called fair use. Fair use provides a sort of family of exceptions to that copyright exclusivity. It's really critical for balancing the rights of creators with the public interest in allowing things like education, commentary, and innovation.
So what kinds of things fall under fair use?
Well, the classic examples are using copyrighted material for purposes like academic research, news reporting, criticism or commentary, scholarship, teaching, parody, or satire. There are also some more practical exceptions, often considered fair use, like making a personal backup copy of software you legally purchased, or creating a version of a work that's accessible for people with disabilities. It's a complex legal doctrine, but essential to know about. And in the digital world, you really can't talk about copyright without mentioning the Digital Millennium Copyright Act, the DMCA in the US.
Ah, yes, the DMCA, passed back in 1998.
That's the one. It was heavily pushed by the entertainment industry, largely to combat the piracy of things like music and movies online. They were particularly concerned about protecting encrypted content, like the Content Scramble System, or CSS, used on DVDs back then. The DMCA infamously made it illegal to create or distribute software or tools designed to circumvent technological protection measures, basically. Anti-encryption software, like the notorious DCSS tool that broke DVD encryption.
Even if the purpose was legitimate, like research.
Even then, yes. That part was and remains highly controversial. But arguably the most lasting and often abused legacy of the DMCA is the takedown notice process.
Right. Explain that again.
Under Section 512 of the DMCA, there is a safe harbor provision for online service providers, like web hosts or platforms like YouTube. To qualify for this safe harbor from liability for copyright infringement by their users, they have to follow certain rules. One key rule is that if a copyright holder sends them a formal notice alleging that specific content hosted on their platform infringes their copyright, the provider must act expeditiously to remove or disable access to that content.
Just based on an allegation?
Essentially, yes. The burden of proof immediately shifts to the person who posted the content. They then have to file a counter notice stating under penalty of perjury that the material was removed by mistake or misidentification, or that it qualifies as fair use.
Wow. So the content comes down first and you argue about it later.
That's the practical effect. And this process has fundamentally changed online content governance. It's frequently criticized for being weaponized, used not just for legitimate copyright claims, but sometimes to silence critics, remove negative reviews, or gain a competitive advantage by taking down rivals' content, at least temporarily. It requires constant vigilance and often legal resources to deal with improper takedown notices.
Okay, DMCA takedowns, got it. Moving on from copyright. What's next?
Next, we have trademarks. Trademarks protect things like words, names, symbols, logos, sounds, even colors that are used to identify and distinguish the goods or services of one party from those of others. It's all about protecting brand identity and goodwill in the marketplace.
Like company logos or product name.
Exactly. Think the Nike swoosh, the Coca-Cola script, the name Google. If you register your trademark with the relevant government body, like the U.S. Patent and Trademark Office, USPTO, you can use the symbol. If you're just claiming common law rights or state registration, you might use U or SM for a service mark.
And how long do trademarks last?
Unlike copyrights and patents, which have fixed terms, trademarks can potentially last forever as long as the mark continues to be used commercially to identify those goods or services. You have to actively use it and renew the registration periodically.
Okay. Third type.
Third is patents. Patents protect inventions. This could be a new machine, a manufacturing process, a chemical compound, or even certain types of plants. Registration with an office like the USPTO grants the patent owner exclusive rights to make, use, sell, and import the invention for a set period.
And that period is usually?
Typically around 20 years from the date the patent application was filed. For coordinating international filings, the World Intellectual Property Office, or WIPO, plays a significant role.
All right. Copyright for expression, trademark for brand, patent for invention. What's the fourth one?
The fourth type is trade secrets. Trade secrets protect confidential business information that provides a competitive edge. This could be a formula, like the recipe for Coca-Cola, a manufacturing process, a particular method of doing something, customer lists, or other valuable compilations of information.
What's the key difference here compared to patents or copyrights?
There are two huge distinctions. First, protection for a trade secret arises automatically upon its creation without any registration, similar to copyright in that respect. However, and this is critical, the information must be kept secret. If the owner fails to take reasonable steps to maintain secrecy, maybe through inadequate security controls, or not using non-disclosure agreements, or just letting the info leak out, they lose the trade secret protection entirely. Secrecy is paramount.
Okay, so no registration, but you have to actively protect it. What's the second distinction?
The second major difference is that trade secret protection does not grant market exclusivity in the same way a patent does. If a competitor independently develops the same process or formula through their own legitimate efforts, or if they manage to reverse engineer your product legally, they are perfectly free to use that information. Trade secret law only protects against misappropriation, like theft or breach of a confidentiality agreement. It doesn't stop independent invention.
Got it. That's a really important difference. Okay, so circling back to IRM tools, how do they actually enforce these rights in practice? There are different methods, right?
Yeah, there are various ways IRM tries to enforce policies. Some are pretty basic, like rudimentary reference checks, which might just be looking for a license file or relying on users consulting a manual not very strong. Then you have things like online reference checks, where software phones home to verify a product key or subscription status. Local agent checks are common, where a piece of software running on the user's machine enforces the rules. Think about gaming engines that prevent cheating or modification. You also see licensed media presence, where the software checks if the original CD or DVD is in the drive, though that's less common now. And support-based licensing, where access to essential updates or support is tied to a valid license.
But for a really robust IRM solution, especially thinking about protecting sensitive corporate data in the cloud, there are some core functional requirements it absolutely needs to meet.
Definitely. A strong IRM system needs persistent protection. The controls have to stick with the content. They have to follow it no matter where it's copied, moved, or stored on a laptop, a USB drive, in cloud storage.
Okay, it travels with the data.
Right. It needs dynamic policy control, meaning the data owner has to be able to modify access rights and permissions instantly, even after the data has been distributed. Automatic expiration is crucial. Access should automatically cease when a license expires, or when a legal retention period is up, or maybe after a set time period defined by policy.
That prevents stale access.
Exactly. It needs continuous auditing, logging who is accessing the data, what they're doing with it, and any attempts to violate the policy. Replication restrictions, the ability to control whether the content can be copied at all, or maybe how many copies can be made. And finally, remote rights revocation. The owner needs the ability to instantly revoke access rights for a specific user or document, even if that data is sitting on a remote machine or device they don't control. This is vital during disputes, employee termination, or litigation.
Those sound like powerful capabilities. But deploying these kinds of sophisticated IRM tools in the cloud, that seems like it would cause some headaches. The book mentions 4 main conflicts.
Yeah, implementing strong IRM in a typical cloud environment runs into some significant technical friction points. 4 main ones stand out for the CCSP. First, there's a conflict with replication restrictions. IRM often demands strict file-level consistency and tight control over every single copy. But cloud infrastructure, especially things like object storage, often relies heavily on eventual consistency and automatic replication across different servers, availability zones, maybe even regions, to ensure high availability and resilience.
So the cloud is making copies the IRM can't track.
Essentially, yes. These core cloud mechanisms that are great for availability can directly undermine IRM controls that expect to manage every instance of a file. The IRM might lose track or be unable to enforce policy across all those dynamically replicated blocks it doesn't even know exist.
Okay, what's the second conflict?
Jurisdictional conflicts. If your IRM solution is trying to enforce policies based on intellectual property laws tied to a specific physical location or country, but the cloud provider is dynamically moving the underlying data blocks between server farms in different countries, maybe for load balancing or cost optimization, often without the data owner's direct knowledge, the legal validity and enforceability of that location-based IRM control can become questionable, or at least very complex. The owner simply might not know where their IP is physically residing at any given moment.
Right, the where's my data problem again. Third conflict.
Third is agent enterprise conflicts. As we mentioned, many IRM systems rely on installing local software agents on the endpoint device to enforce the policy. These agents often struggle to work reliably or consistently with modern cloud computing delivery models. Think about virtual desktops, VDI, desktop as a service platforms, or complex bring your own device, BYOD scenarios, where the company doesn't fully control the endpoint. Getting the agent installed, updated, and working correctly across all those diverse platforms can be a nightmare, leading to interoperability issues and enforcement gaps.
Yeah, I can see that being messy. And the fourth conflict.
Fourth is API conflicts. Since IRM is often deeply embedded within the content itself, trying to access or process that IRM-protected material through various applications or platforms using standard cloud APIs can sometimes lead to problems. It might cause performance degradation because of the overhead of the IRM checks, or in some cases, the API interaction might just fail outright if the application isn't fully IRM aware. This can hinder legitimate business processes that rely on programmatic access to data.
Okay, those are some significant challenges to consider when trying to use IRM in the cloud. So let's move towards the end of the data lifecycle. We've classified it, protected its IP value. Now we need to manage those final phases: store, archive, use, and especially destroy. This means we need comprehensive policies covering retention, audit, and disposal. The book notes these can sometimes be grouped under one big data management policy, but they still need their own specific, granular details.
Absolutely. You need clarity on each aspect. Let's start with data retention. The data retention policy dictates the retention periods, basically, how long different types of data must be kept in archive before they are allowed to be destroyed. This isn't usually an arbitrary decision. It's often driven by legal requirements, regulatory mandates, like tax laws, healthcare regulations, or maybe contractual obligations. So the policy document itself must clearly address all applicable regulations, and critically, it needs to explicitly outline a procedure for resolving conflicts.
Conflicts like?
Like if state law A says you must keep customer records for 5 years, but maybe federal regulation D says destroy related records after 3 years to protect privacy. Which rule wins? The policy needs a clear hierarchy or process to determine the governing requirement, which is usually keep it for the longest required period. The policy also needs to define acceptable retention formats. What type of media should be used for long-term archives? Tape, optical disc, specific cloud storage tiers, and what level of encryption is required while the data is in that long-term storage.
And you mentioned testing earlier.
Yes. Critically important. The policy must include detailed archiving and retrieval procedures. And part of that procedure absolutely has to be periodic testing of the recovery process. It is genuinely shocking how many organizations diligently back up and archive petabytes of data for years, but never actually try to restore it until there's a real disaster or a legal request. Only then do they discover the tapes are unreadable, or the encryption keys were lost, or the process just doesn't work. Testing recovery is non-negotiable.
Okay. And within retention, there's one rule that trumps all others, right? The legal hold.
The legal hold, also sometimes called a litigation hold or preservation order. This is absolutely paramount. It's a requirement usually triggered by notification of impending or actual litigation, or maybe a government investigation that immediately requires the organization to suspend all relevant data destruction activities.
It pauses the destruction clock.
Completely. The legal hold overrides all other data retention policies, standard operating procedures, contractual agreements, even potentially conflicting laws like HIPAA that might otherwise mandate data destruction after a certain period. If data falls under a legal hold, you must preserve it until the hold is lifted by legal counsel. Violating a legal hold can have severe legal consequences. It's an immediate mandatory pause on the destroy phase for specific data.
Gotcha. Legal hold is king. Now, what about the risks of retention in the cloud?
A major cloud-specific risk is actually the flip side of destruction. Ensuring the provider stops retaining your data beyond the required retention period when it's supposed to be disposed of. Think about it from the provider's perspective. Their entire business model, their SLAs, are fundamentally designed around never losing data. They build in massive redundancy, replication, backups, snapshots. Persistence is key for them.
So getting them to definitively delete something is hard.
It can be, yes. Contractually forcing them to guarantee that they have securely and permanently disposed of all copies of your data at the end of a specific retention window, especially in a complex multi-tenant environment where your data blocks might be intermingled with others, is a significant challenge. This needs to be meticulously detailed and negotiated in the contract and the DPA, including verification mechanisms.
Okay, that makes sense. So after retention comes data audit. This is about regularly reviewing data usage, its condition, the controls around it, to ensure compliance with policies and regulations. And the audit policy applies across all phases of the data lifecycle, right? Not just storage.
Correct. Auditing touches everything from creation controls to destruction verification. The audit policy document itself needs to define things like audit periods, how often, the scope, what systems or data types, and the specific processes to be followed. And crucially, it must clearly define responsibilities for conducting the audits. And a key principle here is to actively avoid conflicts of interest. Meaning the auditors, whether internal or external, should not report directly to the management structure that owns or operates the systems or data they are auditing. Their reporting line needs to be independent, maybe to a board committee or a separate compliance function. Otherwise, the credibility and objectivity of the audit findings are immediately compromised.
Makes sense. Independence is key. Now, auditing relies heavily on logs, but you mentioned log analysis is difficult.
It really is, for several practical reasons. First, log review is often treated as an additional duty assigned to already busy IT or security staff. It becomes a low priority, easily skipped when things get busy. Second, let's be honest, reviewing massive volumes of logs is often a highly mundane and repetitive task. This leads to significant analyst fatigue, burnout, and the potential for mistakes or missing subtle indicators. And third, finding the right personnel is tricky. You need someone junior enough, perhaps, that you can assign them this repetitive task, but simultaneously experienced and knowledgeable enough to actually spot the one subtle unauthorized activity hidden within millions of lines of perfectly normal authorized activity. That's a difficult balance to strike.
And there's also a risk in logging too much.
Absolutely. There's often an instinct to just log everything, just in case. But that's a dangerous path. First, it creates massive storage costs. You might end up needing a storage system nearly as large as your primary production systems just to hold all the logs. But worse, think about what you've created. That massive aggregated collection of detailed log data showing who accessed what, when, from where, maybe even what commands they ran, immediately becomes an incredibly high-value target for an attacker.
So the logs themselves become a security risk.
Precisely. You've created a new, vast attack surface. If an attacker compromises your log management system, they potentially gain a roadmap to your entire environment and sensitive data. So you need a balanced logging strategy log, what's necessary for security and compliance, but not necessarily every single trivial event, and protect those logs robustly.
And the cloud adds another layer of difficulty to auditing.
It can, yes. The challenge often lies in getting the necessary log data from the cloud provider. Depending on the service model, AS, PaaS, SaaS, and the specific provider, they may be unable, or sometimes even unwilling, to disclose highly granular system-level or infrastructure logs to individual customers.
Why wouldn't they?
Several reasons. Liability concerns, protecting their own proprietary operational details from competitors, or simply the sheer operational complexity and cost of isolating and providing detailed logs from their shared multi-tenant infrastructure for thousands of customers.
So you need to sort this out up front.
Absolutely. Your specific logging and audit requirements, including access to provider logs, must be clearly negotiated and explicitly written into the Contract and Service Level Agreement, SLA, before you migrate significant workloads to the cloud. Don't assume you'll be able to get the logs you need later.
Okay, retention audit. That brings us to the final step. Data destruction disposal, the destroy phase.
Right. Getting rid of data securely when it's no longer needed or permitted to be retained. In a traditional environment where the organization physically owns the servers and storage hardware, we have several well-established options. The preferred method is usually physical destruction. If you shred, pulverize, burn, or drill holes through the hard drive or storage media, the data is definitively gone. It's verifiable.
Can't argue with a pile of metal shavings.
Pretty much. Another method for traditional magnetic media, like spinning hard drives or tapes, is degassing. This uses a powerful magnetic field to scramble the magnetic domains on the platters, effectively erasing the data. But, and this is crucial, degassing does not work on modern solid-state drives. SSDs, which don't store data magnetically.
Okay, so degassing is out for SSDs. What about overwriting? Writing patterns over the data.
Overwriting, sometimes called wiping or sanitization, involves writing patterns of random data, like zeros, ones, or specific characters, across the entire drive, usually multiple times or passes. This has long been a standard practice. However, it's very time-consuming for large drives. And more critically, standard overwriting techniques are now widely considered ineffective on modern SSDs.
Really? Why is that? I thought overwriting was the standard.
It was for HDDs, but SSDs work differently. First, remember that simply deleting a file in the operating system usually just removes the logical pointer in the file allocation table. The actual data bits often remain on the drive until they are eventually overwritten by new data. That's not secure disposal, but the bigger issue for overwriting SSDs comes down to internal drive mechanisms like wear leveling and garbage collection.
Explain those quickly.
Sure. SSDs use flash memory, which has a limited number of write cycles per memory cell. To extend the drive's lifespan, the internal SSD controller constantly shifts data blocks around, trying to distribute the writes evenly across all the cells that's wear leveling. Garbage collection is the process where the controller cleans up blocks that are marked for deletion but still contain old data, making space for new writes.
So how does that break overwriting?
When your operating system sends a command to overwrite, say, logical block address 5, the SSD controller might intercept that command. Because of wear leveling, it might decide to write the new data to a completely different physical block, maybe physical block 7, which was previously empty or marked for garbage collection. It then updates its internal map to say logical block 5 now points to physical block 7 and marks the original physical block 5, which still contains your sensitive data, as stale or available for garbage collection later.
So the overwrite command might not actually overwrite the physical location where the original data resides?
Exactly. Your sensitive data could remain intact in that original block, potentially accessible to sophisticated forensic techniques or attackers who can bypass the controller, until the drive controller eventually gets around to garbage collecting that specific block, which might not happen immediately or predictably. Standard OS-level overwrite commands don't provide reliable sanitization on SSDs.
Wow. Okay, that's a critical point. So given these limitations, especially with SSDs being common now, and the fact that in the cloud we don't own the hardware, how do we securely destroy data?
Well, you've hit the nail on the head. Nearly all those traditional methods become impractical or impossible in a public cloud environment. Physical destruction. You don't own the hardware, and the provider isn't going to let you into their data center with a drill or a shredder. Plus, your data is likely spread across multiple physical devices anyway. Overwriting. Impractical due to the SSD issues we just discussed, the lack of direct hardware access, the unknown physical location of all data blocks, and the complexities of multi-tenancy. You can't securely overwrite storage space that might be shared, even logically separated, with another customer. Degaussing is irrelevant for most cloud storage.
So what's left?
This effectively leaves one primary, pragmatic, and cryptographically verifiable option for secure data disposal in the cloud. Crypto shredding, which is also sometimes called cryptographic erasure.
Crypto shredding. Okay, define that process.
The concept is actually fairly elegant. First, you ensure that the data you want to eventually destroy is encrypted using a strong, unique encryption key. Let's call this the data encryption key, or DK. Then, instead of trying to encrypt the massive volume of data directly, you encrypt the DK itself using another key often called a key encryption key, or KEK. Finally, when it's time to destroy the data, you don't bother trying to touch the petabytes of encrypted data blocks scattered across the cloud. You simply securely destroy the relatively small key.
Wait, hang on. Why the two layers? Why encrypt the first key with a second key, KEK? Why not just destroy the DK directly?
That's a great question. It's primarily about speed, manageability, and certainty, especially when dealing with very large volumes of data or many different keys. Imagine you have 10 petabytes of data encrypted with a single DK. Securely destroying that DK might involve complex key management operations. Now imagine you have thousands of smaller data sets, each encrypted with its own unique DK. Managing and securely destroying thousands of individual DKs precisely when needed becomes a significant challenge. By using a KEK to encrypt all those DKs, you centralize the destruction point. When it's time to dispose of the data, you only need to securely destroy the one KEK.
And once that key is gone,
Once the KEK is irretrievably destroyed, all the DKs that it encrypted instantly become useless cryptographic noise. They are mathematically impossible to recover. And without the DKs, the underlying encrypted data remains permanently inaccessible ciphertext effectively destroyed. This allows for near-instantaneous, verifiable cryptographic sanitization of massive amounts of data by destroying just a small amount of key material. It fulfills the requirement for rapid and definitive data disposal in environments where physical destruction or reliable overwriting isn't feasible.
okay, that makes perfect sense. Crypto shredding via key destruction. So the data disposal policy needs to specifically mandate this.
Yes. The policy must detail the required process mandating strong encryption from the start, specifying the use of DTAKEs and key plans, or equivalent key wrapping, and outlining the secure process for destroying the key takes. It also needs to reference all applicable regulations regarding data sanitization and provide clear executable direction on when destruction must occur, for example, end of retention period, termination of service, while ensuring a proper chain of custody and verification process for the key destruction itself.
Fantastic. That clears up the cloud destruction challenge significantly.
Yeah.
All right, we have covered a massive amount of ground today, a really deep dive into the technical, the legal, the operational nuances of cloud data classification and management. Let's try to boil this down and recap the absolute essential takeaways for everyone listening, the things that must stick.
Good idea. Let's hit the highlights.
Okay, number one for me, master that critical difference between the data owner or data controller. They set the policy, they carry the ultimate legal liability, even down the supply chain, and the data processor, often the cloud provider, who applies the controls and executes actions on behalf of the owner. Know who holds the risk.
Number 2, remember the full data lifecycle. Create, store, use, share, archive, destroy. And critically, remember that the initial classification, the labeling, the owner identification, that must happen right at the start during the create phase. Don't play catch-up.
Number 3, really understand that technical distinction we hammered on between categorization, which is based on use, like regulatory compliance or business function, and classification, which is based on an inherent trait like sensitivity, jurisdiction, or criticality. That separation dictates both the scope of your policies and the level of security controls you apply.
Number 4, be fluent in those 4 main types of intellectual property protection. Copyright protects the tangible expression of an idea. Patent protects the invention itself. Trademark protects the brand identity. And trade secret protects valuable confidential information, but only if you maintain active, mandatory secrecy. And remember, it confers no market exclusivity against independent discovery.
Number 5 is crucial for the cloud. Recognize why traditional data destruction methods like simple deletion or standard overwriting often fail, especially on modern SSDs due to wear leveling and garbage collection. Understand that because we lack physical control and face multi-tenancy, crypto shredding, cryptographic erasure via key destruction, becomes the primary, pragmatic, and verifiable disposal method in the cloud.
And finally, number 6, never forget the absolute supremacy of the legal hold. It is a paramount legal requirement. When issued, it immediately stops all data destruction activities for the relevant data, superseding every other retention policy, destruction schedule, or even conflicting law. Preservation becomes the mandatory priority.
Excellent recap. Owner versus processor, lifecycle phases, categorization versus classification, IP types, crypto shredding, and legal hold. Got it.
You know, stepping back, data classification really isn't just some academic exercise or a compliance checkbox. It truly dictates your entire cloud security strategy and operational approach. If you don't classify accurately, if you don't know the sensitivity or criticality of your data, you're basically forced into treating every single piece of data as if it were top secret, mission critical, and subject to the strictest possible regulations like GDPR.
Which, as we said at the start, is just impossible.
Exactly. That approach is financially crippling and operationally unsustainable. Proper classification is the only rational way to strategically and effectively apply your limited security resources, your budget for encryption tools, your staff time for auditing, your spending on secure storage and retention where they're genuinely needed and will have the most impact.
And we certainly touched on how those complex, often conflicting multinational jurisdictional requirements, especially around PII, and the different global privacy models like GDPR versus the more sector-specific U.S. laws, create an environment that demands constant vigilance, ongoing monitoring, and often specialized legal consultation. It's a challenge that absolutely never stops evolving. You have to stay current.
Couldn't agree more.
But the good news is, now that we have a solid grasp on what our data is, who owns it, its value, and how to manage its full life cycle, from creation right through to cryptographic destruction. Well, the next logical step is figuring out how to secure its boundaries and protect it while it's moving around. And that takes us neatly into the next area. Cloud data security. We'll be looking specifically at techniques for encrypting data in transit, securing data across different network boundaries, managing encryption keys effectively, and much more. That's where we'll pick up next time.